Okay, so now we move on to an application of all these previous results to Gaussian measures. Okay, so let's recall first of all that a Gaussian measure, let's call it P on Rn with covariance C, has the following density. Okay, we're actually in this particular case, without loss of generality, we assume that the covariance matrix is it's strictly positive, or the determinant of C is not zero. Now, if the determinant of C is zero, it just means that our probability measure is concentrated on some proper linear subspace of Rn, and so we can simply restrict ourselves to that subspace. And because in the concentration inequality, the distance from a point to a set, well, it will be the same distance as in the ambient space. I mean, if you prove the result on the subspace, it's the same result that we want. And so without loss of generality, we can assume that we're already on this proper subspace, so the covariance matrix is non-degenerate. In particular, we will write this density above as E, so to the minus V of x. Okay, so it will be convenient just to keep it this simple notation where V of x will be the quadratic form in the exponent. Okay, and then plus some constant. So we can take this constant in front of the exponent inside and just think of it as some constant that depends on this covariance matrix C. Okay, and before we state our main result here, we will notice that the quadratic form has the modulus of convexity given by the same quadratic form, just with some constant. Okay, so what this means is that this function v of x is obviously convex, and in particular, if you take some parameter t between 0 and 1, and then you compare the linear combination or convex combination of v of x and v of y, right, this should be greater or equal than v at the convex combination of x and y. Okay, but in this particular case, you can just plug in and simplify. So I'm going to skip this calculation, but if you just expand these quadratic forms, you will see that this is equal to t 1 minus t times this quadratic form on x minus 1, on x minus y. Okay, and what we will use below is that this is greater or equal than t 1 minus t divided by 2 times the largest eigenvalue of C. Okay, times the distance between x and y squared. Okay, so we simply took the smallest eigenvalue of the inverse of C, which is just 1 over the largest eigenvalue of C. And so we wrote that the modulus of convexity of this quadratic form V can be controlled from below by this expression here. And so this observation will be important in the next proof. Okay, and the main result that we will prove right now, from which the concentration inequality will follow by a pretty straightforward, of course very clever, by pretty straightforward observation, will be the following theorem. Okay, this is known as Talleyrand's quadratic transportation inequality, or Talleyrand's quadratic cost transportation inequality. Okay, so if we consider as above this Gaussian distribution on Rn, and then we consider some other probability measure which is absolutely continuous with respect to P. Okay, so it has some density with respect to P such that the integral of the a norm of x squared with respect to this measure q is finite. Okay, then we will show that the Wasserstein distance W2 between q and p is bounded by the square root of 2 times the largest eigenvalue of the covariance matrix times the Kullback-Leibler divergence between q and p. And the assumption that the norm squared is integrable with respect to q is the same assumption that we required in the definition of the Wasserstein metric W2. Alright, so first we start with the definition of this Wasserstein distance W2, and we recall that W2 squared was the infimum of the integral of the distance squared with respect to all measures mu with marginals p and q. Now, before we apply Kantarovich-Rubinstein theorem to this, it will be actually important to just rescale things a little bit. So here we will multiply and divide by a constant k. So in front of the infimum we put 1 over k, and inside the infimum we multiply this distance squared by k. Okay, and in particular the Kantarovich-Rubinstein theorem will apply to any k, but let me just point that later on we'll use any k less than 1 over 2 times the largest eigenvalue of c. Okay, but for now, the Kantarovich-Rubinstein theorem tells us that so 1 over k, we'll just leave it as it is, but this infimum can be written as supremum, right? We have the duality where you can write this as a supremum of the sum of integrals f dp with respect to p plus g with respect to q, and these two functions f and g should be continuous functions on our space, and they should satisfy the condition that f of x plus g of y should be less than whatever plays the role of the distance. And in this particular case, because of this rescaling, this plays the role of d in the proof of Kantarovich-Rubinstein theorem, right? So here the condition is that this sum is less than k times the distance between x and y squared. So now we have used the Kantarovich-Rubinstein theorem, and so in order to prove this result that we are trying to prove here, instead of the definition, instead of the infimum, now we will try to control this supremum, and we'll see that it can be bounded by exactly this square root of Kullback-Leibler divergence. So somehow we need to use this condition here on this pair f and g, right? And we have to use this condition in order to control the sum of these two integrals. And so we will use this condition together with Prekopa-Landler inequality to show that for any pair of f and g like this, that we will show that the following inequality holds for any pair f and g like here. So namely integral of e to the g plus integral of f with respect to p. So this integral of f with respect to p just appears as a constant inside this exponent. And then you integrate this function with respect to p, and we'll show that this is less than or equal than 1. Okay, so this will be a consequence of this condition on f and g, that their sum f of x plus g of y is bounded by this constant k times the distance squared. Okay, but before we show this, let's conclude using the variational representation for the Kullback-Leibler divergence. Okay, namely here, if you take this pair f and g and denote by v of x this g of x plus this constant integral of f with respect to p. So in other words, this is the function that appears here. Right? So in other words, what we will prove is that integral of this function, integral of e to v with respect to p, is bounded by 1. Okay? And then the variational representation for the Kullback-Leibler divergence tells us that integral of v with respect to q is then bounded by this divergence between q and p. So here we use the variational representation above. But the integral on the left hand side here is just integral of f with respect to p plus integral of g with respect to q. Okay, so that's exactly the quantity that we are trying to maximize on the right hand side of this Kantarovich-Rubinstein theorem. Okay? And so in other words, for any pair f and g, we have the condition that together with this variational representation implies that the sum of the integrals is bounded by this Kullback-Leibler divergence. So as a result, if you combine all together and go back to where we started, we get that W2 between P and Q squared is bounded by, well, we have this constant 1 over K in front, and the supremum is bounded by this divergence. Okay, and the K, as I said, at some point we will need that K is less than 1 over 2 times the largest eigenvalue. So in particular, 1 over K is anything bigger than anything bigger than twice the largest eigenvalue. So since this inequality is true for any such K, we also get inequality with twice the largest eigenvalue. Okay, and that's exactly what we want. So what remains is to show how the Prekopa-Landler inequality can be used in order to show that for any pair of f and g, here you have this inequality for this integral. And this is where the modulus of convexity appears, because in this condition, f of x plus g of y is less than or equal than k times x minus y squared, we have exactly this distance squared which appears on the right hand side in this modulus of continuity calculation. Okay, so if we go back here, the only thing that is missing is this factor t times 1 minus t. Okay, so here, first of all, k was less than 1 over twice the largest eigenvalue of c, and then if we multiply both sides of this inequality by t times 1 minus t, then on the right hand side you will get exactly the right hand side of the modulus of continuity above, which will be bounded by, okay, and then let's collect the terms that only have x first. So you have t times 1 minus t f of x, and then you have on the other side this t times v of x. Okay, then let's collect everything that has y as a variable. So we have 1 minus t times g of y, and on the other side we have this 1 minus t times v of y. Okay, and what is left is minus v of tx plus 1 minus ty. Okay, then we take exponent of both sides, so here you have e to this first term times e to the second term, and this is bounded by e to the minus v on the right hand side. And then we think of this first factor here as some function u of x to the power t, and then the second factor, we think of this as some function v of y to the power 1 minus t, and the right hand side we just think of this as w at the convex combination tx 1 minus ty. So we get exactly the condition between three functions u, v, and w in the Prekopa-Landler inequality. Okay, and so Prekopa-Landler inequality implies that the integral of u to the power t, right, times integral of v to the power 1 minus t is bounded by integral of w, where integral here is everywhere is with respect to the Lebesgue measure dx on Rn. But then, if you see, what are we integrating here? We are integrating e to the 1 minus t f of x, and then e to the minus v of x dx, right? This e to the minus v is exactly the density of the Gaussian measure, so this is just integral with respect to the Gaussian measure. Okay, so this is to the power t, and then the second term you're integrating e to the t g of y, again e to the minus v of y dy, but this is the integral with respect to the Gaussian measure, so this comes to the power 1 minus t, and on the right hand side you just integrate e to the minus v of x dx, which is just the integral of the Gaussian density, which is 1. Okay, so in other words, what we get is integral of e to the 1 minus tf of x with respect to the Gaussian measure p to the power t, and then integral e to the t g of x with respect to the same Gaussian measure to the power 1 minus t is bounded by 1. Right? Now we take a power 1 over t and 1 over 1 minus t, so that the first integral will be 1 minus t, or LP with p equals to 1 minus t, norm of e to the f of x. And the second will be the same integral to 1 over t. Okay, and this is less than or equal than 1. And then we send t to 1. So we take a limit t goes to 1. The second term here will converge, at least formally. This will be, if you replace t by 1, this is just integral of e to the g with respect to this Gaussian measure. Okay, and then when you send t to 1, 1 minus t goes to 0, and it's a simple exercise using L'Hopital's rule to see that this is just integral of e to the integral of f with respect to p. Actually, when I chose this constant k above to be smaller than 1 over 2 to the 1 over 2 times the largest eigenvalue of c, I had in mind that this might be useful here to justify this convergence in the second integral. And I was thinking about using a dominated convergence theorem because, you know, if you remember the condition on that f of x and let's take x to be 0. So f of 0 plus g of y should be less than or equal than this k times x minus y squared. And if x is 0, this is just y squared. So in other words, this function g can at most grow quadratically, and if we put the constant k to be small enough, then the density of the Gaussian actually would dominate here, and you would have dominated convergence theorem. But now I realize that we could just use a monotone convergence theorem here. So from the beginning we could have chosen k to be just equal to this constant, right? Because in this second term we essentially have a dominated convergence theorem, because we can break this integral e to the t g of x into two pieces. Okay, we can consider one piece where g is negative, and on this piece e to the t times g of x is just bounded by 1. So on this piece you just have a dominated convergence. And then on the complement, when g is positive, then you have monotonicity, because e to the g will be bigger than 1. So e to the t g of x on this set will be increasing to e to g of x as t is increasing to 1 here. And so for this piece we can just use a monotone convergence theorem. And so actually just with the constant k equal to 1 over 2 times the largest eigenvalue, when we pass to the limit, we get what we want, right? We get that the e to the integral f dp times integral of e to the g is bounded by 1. And by the way, of course, in the first term you need that this integral is defined, but that's for a simple reason. Then f grows at most quadratically with x, right? By just like I explained that g grows quadratically with y, f grows at most quadratically in x, and you integrate with respect to Gaussian. So of course this is well defined. Okay, so Prekopa-Landler gives us this inequality, which of course we can rewrite as integral of e to the g plus this constant integral of f with respect to p, and then conclude the proof of this inequality. Alright, so now that we have this Talagrand's quadratic cost transportation inequality, we can finally use it to prove the Gaussian concentration inequality that I chose as a motivation for this whole section in the beginning. Okay, let me remind you that the theorem that we are trying to prove is that when our measure P is the Gaussian measure with covariance C on Rn, and you take some measurable set A with a positive measure, then the probability of the set of x's which are at least at a distance t from the set A will become small very fast with this distance t, right? So it will be 1 over probability of A times e to the minus t squared over 4 times the largest eigenvalue of C. That's what we want to prove. And then the proof goes as follows. Okay, we consider PA to be a conditional distribution on the set A. So in other words, probability PA of C will be this Gaussian probability of C intersected with A over the probability of A. In particular, this is absolutely continuous with respect to P, and the density is obviously just this constant 1 over P of A on as long as you stay on the set A, so times the indicator of A. So outside of the set A, the density would be 0 because the probability there would be 0. And in particular, the Kullback-Leibler divergence of this conditional distribution from this Gaussian, just by definition, it's integral of the logarithm of the density, so 1 over P of A with respect to P of A, and we are integrating a constant here, so this is just log of 1 over P of A. Okay, so we can see that in this particular case we can compute this divergence explicitly and easily. Then if we take two sets A and B, and at this point we want to use this Lagrange inequality that we just proved, but we'll consider two sets A and B, and we'll consider the Wasserstein distance between this conditional probability PA and conditional probability PB. And at this point, first we use the fact that this W2 is a metric, so you can apply first the triangle inequality. So you can look at the distance to the Gaussian P. Right, and then use this comparison where W can be bounded by the square root of twice largest eigenvalue of the covariance matrix times the square root of the divergence, but the divergence is just this log of 1 over the probability of the set A, so then you take square root, and the same for the set B, so square root of the log of 1 over P of B. Alright, and then we use the inequality that square root plus square root is less than square root of twice the sum. So here we can bound it from above by square root of 4 times the largest eigenvalue times the square root of the sum of logs. So this will be just the square root of the log of 1 over P of A times P of B. Now on the other side, when we look at this Wasserstein distance, in the case when B is the set of points which are at least at a distance t from A. So let's consider this particular set that we were interested in the Gaussian concentration inequality, and then ask ourselves what is this transportation distance between the measure PA concentrated on the set A and the measure PB, which is concentrated on the set at a distance t from A. Okay, and if you remember this interpretation of average transport cost of moving one pile of mass into the other, you should realize that we are moving each point at a distance at least t. So this average will also be at least t. Of course, in this definition, W was the square of the distance, so you move it at a, when you move, you average something that is bigger than t squared, but at the end we take a square root, so we get something greater or equal than t. Okay, so this is just from a heuristic interpretation of our W2 metric, but of course you can also make this clean and rigorous just by recalling that you try to find the infimum here of the integral x minus y squared d mu, and then at the end we'll have to take a square root, and you minimize this over all measures mu with marginals P of A and P of B. Right, and the fact that the marginals concentrate by our construction on these sets A and B, so in other words P of A as weight 1 on the set A and P of B as weight 1 on the set B. Right? That means that this any measure mu with these marginals is concentrated on A times B, on this rectangle A times B, right? Because outside of this rectangle, either the first coordinate is not in A, which has measure 0, or the second coordinate is not in B, which also has measure 0. Okay, so in particular, when we minimize this integral, the integral itself can be restricted to the rectangle A times B, right? But on this rectangle, the distance between x and y is bigger than t, right? So in fact, the integral will be greater than t squared, and then we take the square root. Okay, so we see that the Wasserstein distance here is greater or equal than t. And so if we go back, what did we show? We showed that t is less than or equal than this square root on the right hand side, and then we solve this inequality for the probability of b. So if you just square and take the exponent of both sides, you will get that p of b is less than or equal than 1 over p of a e to the minus t squared over 4 times the largest eigenvalue of c. Okay, and if you recall the definition of the set B, it was all points at the distance at least t from A. That's exactly what we wanted to prove. Okay, so that finishes the proof of this Gaussian concentration inequality. Okay, now one comment that I wanted to make here is that actually the result that we just proved would be enough to prove in the case of standard Gaussian distribution with the covariance given by the identity, right? And that's because you can simply make the change of variable. So if your random variable x is Gaussian with covariance c, and then you take a standard Gaussian vector with the covariance given by the identity, right? You can write in distribution x as the square root of c times g. And if you prove the above result for the distance for the standard Gaussian random vector from a given set, so in that case it would be probability that standard Gaussian is in this set and e to the minus just t squared over 4. And as I mentioned before, this is not the optimal constant here. You can replace it by 2, but in any case the general case would be reduced to this, because when you compare, let's say, the distance for x from a set, from any set A, right, you can write it as a distance from square root of c times g from the set square root of c inverse, so c to the minus 1/2 times a. And the distance here, when you scale x and y, when you look at the distance between 2 points, when you scale them by this linear transformation, it will grow at most, or it will grow fastest in the direction of eigenvector corresponding to the largest eigenvalue. So at most this will be square root of the largest eigenvalue of c, right, times the distance between g and this set A, times the shifted by this linear transformation. Okay, and you want to consider when this distance here is greater or equal than some t, so it will be included, right? This event that you're interested in will be included in the event when t over square root of this largest eigenvalue is less than the distance between standard Gaussian and this set. Okay, and then you can see that if you apply the inequality for the standard Gaussian, just this change of variable or this scaling by the square root of the largest eigenvalue gives you the same inequality for a general x. Okay, so that's one quick comment. And another quick comment is that in fact for the standard Gaussian G, or let's call this measure P, you have in some sense an optimal form of this result, which is and the analog of the isoperimetry of the ball with respect to the Lebesgue measure that we discussed at the beginning of this section. Namely, in this case, the role of the Euclidean ball is played by the half spaces. So for the Gaussian measure, you have the so-called isoperimetry of half spaces. Okay, namely that if you have any measurable set, and then if you take a half space with the same probability, here probability is the standard Gaussian. Okay, then half space would have a smaller surface in the same sense as before, that when you grow your set, the volume will, or the measure will grow faster for generic set A compared to the half space. So half space has the smallest surface in the sense of the Gaussian measure rather than the volume. Okay, so of course this particular result in the form of this isoperimetry of half spaces, it's more complicated, and we are not talking about this here, but I just wanted to mention because it's related to what we prove, and just wanted to mention that there is some kind of optimal form of this statement is known here. Okay. All right, and finally, just a couple of words about the ending of this section. I'm not going to discuss this here, but after this you can find another proof of concentration inequality that we just proved using only Prokopy-Landler inequality. And then the last part of this section is about total variation distance between probability measures and its relation to the Wasserstein distance for the discrete metric. So there are some kind of analogs of what we proved for discrete metric. Okay, and the analog of Talagrand's transportation inequality there is given by Pinsker's inequality. But I'm going to end this section here, and so this also concludes chapter 4.